This is TWIS. This Week in Science, episode number 744, recorded on Wednesday, October 23rd, 2019. Don't fear the AI. Hey everyone, I'm Dr. Kiki, and tonight on the show, we will fill your head with a claim, a crisis, and a new record. But first,
TWIS is supported by listeners like you. We thank you for your support. We really couldn't do it without you.
Disclaimer, disclaimer, disclaimer. One of the fundamental rules of defining a human is this. Humans are humans, and anything that is not a human is not human. Seems simple enough, and yet one of the fundamental tendencies humans have is to humanize anything that is not human. And yet, clocks do not really have faces. And when apes show emotions, why, they might be appearing to be human emotions, but it could just as well be that humans are experiencing ape emotions all the time. Somewhere in the in-between, there are truths that may not be comfortable. A face can at times just be a facade that displays information. An emotion can be separated from social context and universal across many species. And while there is no doubt humans have the ability to be intelligent, there is increasing evidence that we are not alone in this. And what is the one thing intelligent creatures of all sorts have in common? They all have a never-ending thirst for more This Week in Science, coming up next.
I've got the kind of mind that can't get enough. I want to learn everything. I want to fill it all up with new discoveries that happen every day of the week. There's only one place to go to find the knowledge I seek. I want to know what's happening, what's happening, what's happening this week in science. What's happening, what's happening, what's happening this week in science.
Good science, you can Blair.
and a good science to you too, Justin, Blair, and everyone out there. Welcome to another episode of This Week in Science. We are back to talk about all of the amazing science that has happened. And I know there are a bunch of scientists out at the Society for Neuroscience meeting this week. I hope you all are having a very brainy time, full of stimulation, so to speak. We don't have that many brain stories, but we are talking about intelligence on the show tonight. Artificial intelligence with Dr. Melanie Mitchell, and we're looking forward to that interview coming up. I also brought stories. What stories did I bring? I have stories about gene editing, a new method, and about a claim from Google about quantum computing. Oh, and elbows. Those are my stories.
Wow, got a lot packed into this show. I brought the simple things, a cosmological crisis that puts the standard model in doubt, question mark, probably not really, and plants, which is exciting by itself.
It is. Plants are one of the best things about this planet. Blair, what's in the animal corner?
Oh my goodness. I have smart crabs, fast ants, and gregarious sharks.
Those are my favorite kind of shark.
Right. I'm just thinking I've never really considered sharks gregarious before, so I'm looking forward to this
will.
You just haven't met enough sharks.
I haven't met the right sharks, obviously.
Yeah.
As we're jumping into the show, everyone, I would love to remind you that if you have not yet subscribed to the podcast, it is available all places podcasts are found: Stitcher, Spreaker, Pandora, radio.com, TuneIn, also on YouTube and Facebook, iTunes, Google, all the places. You can look for This Week in Science. You can also find information at TWIS.org. And now it is time for our interview. I'd love to introduce our guest tonight, Dr. Melanie Mitchell. She is professor of computer science at Portland State University and external professor and co-chair of the science board at the Santa Fe Institute. She attended Brown University, where she majored in mathematics and did research in astronomy, and the University of Michigan, where she got her PhD in computer science. And her newest book is called Artificial Intelligence, A Guide for Thinking Humans. And I like to think that our audience is full of thinking humans. Welcome to the show, Melanie. Thank you so much for joining us tonight.
Oh, thanks. I'm glad to be here.
I'm just going to start off with the big question right off the top, because I know it's at the top of Blair's mind for sure. Do we have to worry about the scary killer AI anytime soon? Is this something we need to worry about?
No. In fact, I think what we have to worry about is more that AI is not smart enough, that it's really too stupid. There's a great quote in my book from Pedro Domingos, who is an AI researcher, who said that, we don't have to worry about machines being too smart and taking over the world. It's that they're too stupid and they've already taken over the world.
And that's kind of a letdown if they're already just not quite enough to do it.
We can't live without them, right? But they're still not very smart.
Right. I mean, the AI that I think most people are familiar with in their everyday lives at this point in time, we've got Alexa and Siri and OK Google, and there's AI that it's becoming more and more prevalent. I'd love to know what we actually mean by AI. What is artificial intelligence when we say these words?
Good question. So different people actually have different definitions, and I go through a few of those in my book. But I would say generally people mean programming computers or getting computers to exhibit behavior that we consider requires intelligence. Of course, we humans aren't totally sure what behaviors require intelligence. We used to think that playing chess at a grandmaster level was the pinnacle of human intelligence. But then we found out that it's not that hard to make machines do that. And then that now seems to be less sort of a definition of intelligence. I think that the definition of AI keeps changing and part of the reason is that intelligence is such an ill understood phenomenon that AI, programming computers to make them more intelligent, helps us understand better what we mean by intelligence or what we don't mean.
Yeah, I mean, we talk every once in a while about intelligence tests. We can't even come up with proper intelligence tests for humans. How would we be able to define that and test it in computers?
Exactly. And intelligence isn't just one thing. It's not one-dimensional. There's social intelligence, there's cognitive intelligence, there's all kinds of different aspects of being intelligent. And it's not clear that I think it's one of those words that is kind of a placeholder for things we don't yet understand. But once we understand things better, we'll be able to replace it with a better set of words.
Right. In the book, I think you use somebody else's word as a suitcase word, where it's just a word that has...
Martin Minsky, one of the AI pioneers, called intelligence and other words like consciousness suitcase words, meaning that they are stuffed. They're like a suitcase stuffed full of different definitions. It's definitely caused some confusion among the public and among AI researchers themselves as to what exactly it is we're trying to study, what counts as AI, what doesn't count as AI. In the beginning, AI really didn't use learning very much. It was based on logic and programming computers to do things like do logical deductions. Only more recently has machine learning become very big and kind of taken over the field. So I think of machine learning as more of a subset of AI.
A lot of the news that we talk about now is machine learning, and not just machine learning, but the deep learning, where you have these massive data sets that the programs are given access to, and then they make connections somehow.
Right. So deep learning just it is a sort of brain-inspired approach to machine learning, where you have what's called a neural network, which consists of simulated neurons that have connections to one another. And when the system is given some, like a photograph or something that a human has labeled as a dog, then the system's supposed to predict that it's a dog, or that it's more likely to be a dog than a cat. And if it's wrong, the connections between neurons get changed, sort of like they do in the brain. Although there's a lot of if there's any neuroscientists listening to this, they'd probably be horrified to hear a computer scientist say this, but it's inspired by the brain. And so these systems change their connections strengths. It's now mostly software rather than hardware. And they learn from lots of examples to do things like recognize dogs in images.
Yeah. So, but isn't the initial problem is that you show it a picture of the dog, and you tell it that this is a dog, and from there on out, it only recognizes golden retrievers as dogs, and any other dog you show it, it's still not a dog until you remind it. No, that even though it's a different breed and it's a different color and it has a different length of snouts to eye ratio, it's still a dog if it's a pug or if it's a black lab or something else. You have to keep informing it at some point until it kind of gets a broad picture of what dog is.
That's right. That's why these networks need huge data sets to learn from, millions and millions of photographs in order to learn these to recognize these kinds of categories. And that's one way they're different from humans in that, like, little kids can learn categories with much fewer examples. And there's a lot of discussion as to why that is and how we can make machines learn from fewer examples. So that's one of the biggest open problems in AI right now.
Yeah, I wonder if by looking at, since this is obviously that there's a lot of the parallels where we're studying intelligence and how the brain is, how it functions and how it's built, right? How the neurons connect to each other and how they allow cognition to occur, and then modeling that in a computer system. How can we synthesize it, so to speak? And I'm wondering if we're really just looking at humans, but do you know if researchers are also looking at other animals and the examples of learning and the ways that other brains learn to see, how these different models of biological wet matter can be all put together to make the artificial?
Right. No, I mean, it's not always the same in all brains, right? But in fact, the deep neural networks today are based on brain research that was actually done in cats to look at how the cat visual system worked. And it turns out that cats have a visual system that's somewhat similar to humans. So it's thought that some of the same things apply.
I'd just be very hesitant to use a solitary hunter as the basis for anything in AI.
Well, AI is nowhere near that.
Yeah,
it's still looking at like how do you go from the retina, light falling on the retina, to saying the word dog or cat, right? Yeah. It's not looking at how I can, a cat or a dog can make up with another cat or dog. Although, that's really important, that whole social aspect. But I'm just saying that deep neural networks are really inspired by, they've largely been inspired by the visual system, but applied in many different areas.
What's closest to your heart? What do you love looking at and working on personally?
What's closest to my heart is the topic of analogy. So this is what I did my PhD dissertation on. And the question is, we make analogies all the time. We see some kind of situation and say, oh yeah, that reminds me of another situation. You tell me that you flew to Austin and they lost your luggage. And I say, the same thing happened to me, but I'm actually talking about a bus ride I took to San Diego, and they lost, some part of my luggage or something. But we just see similarity all the time. And that's really, I think, one of the foundations of how we think about the world. So my work is really focusing on how do we get the concepts into a machine so that it could see those kinds of similarities. So that's what's dearest to my heart. But it's a hard problem. And, I think it's still in its infancy in AI.
Absolutely.
That would be sort of fun, though, if you were interacting with an AI help desk and you like typed in your problem, and and it shot back, yeah, you're up a creek without a paddle. Like, that's what brought me here. Yes,
It's honest, right? It's very honest. Yeah.
I'm just imagining, because there's the analogy issue. It probably brings in all sorts of aspects of context, or depending on what the situation is, versus there's also just things being like each other. And everyone who's taken standardized tests knows this is like this, as this other thing is to, and you have to fill in the blank.
Right.
And are these the kinds of questions that you try and train a computer program on?
So I've worked on things like, how is this particular visual situation like another visual situation? Like, how is walking a dog more like walking a cat, or running with a dog on a bicycle, or things like that? More in the area of visual data. Now, most people, you're right, think about analogy in terms of A is to B as C is to D. Foot is to shoe as hand is to blank.
Right.
Because we all have done those. But analogy goes much deeper. It's kind of like what you mentioned, like, you're up a creek without a paddle. That's like a idiom or a metaphor, if you like. Right. And our language is just filled with metaphors. They're everywhere. We don't even notice them a lot of the time. And a lot of people in cognitive science think that metaphor is really how we think. It's at the core of everything that we do. We say things like, he gave me a warm welcome. And that's like a physical metaphor, because I'm talking about temperature. It's not like the temperature actually went up, but we actually think of it very much in a physical way. So metaphor and analogy are so foundational that we don't even notice them half the time, and so I think that getting computers to recognize and understand metaphors and analogies would go a lot of the way towards making them smarter and more robust.
Then there's the question, though. So once again, coming back to the idea of how the brain works and how we actually are thinking of these things. And there's the idea of the artificial intelligence system giving us some insight into how our brains work. But is it still possible that the artificially intelligent systems can develop in a way that they act similarly to our brains? There's a similar output, but internally the computation is totally different, that it just doesn't match the way that our brains work at all?
Yeah, in fact, that's what happens. I mean, that's where we are now, because even though the deep neural networks are inspired by the brain, they actually work very differently from the brain. All of the information in these neural networks is what's called feed forward, meaning that it goes from one layer forward to another layer, up to some output. So it would be like, it's like information comes into your eye, it goes to the retina, it goes to the first layers of the visual cortex and up through to your, more frontal cortex. But in the brain, that's actually not what happens at all. There's all kinds of feedback. And that feedback is, in a way, what gives us the ability to deal with context and expectation. And that's something that has been very difficult to model using neural networks. People have started working on it, but getting the kind of feedback that we have in the brain is something that's mostly missing from all of the AI that we use today.
I'm imagining an AI Blair running outside, arms outstretched, hearing that it's raining cats and dogs.
Right. Trying to catch those cats and dogs. Yeah.
That's the dream.
Yeah.
Right. Yeah. So in our chat room on YouTube, David De Silva has a question that I was curious about as well. There are some limitations to AI, as the computing power, processing power that we're able to use. This week, there's been a lot of talk about quantum computing. Do you think quantum computing is going to revolutionize AI?
It's possible. I think there's a lot of talk about it. One problem with quantum computing right now is that there's only a limited number of algorithms that it actually improves upon compared with classical computing, and some of them are relevant to AI, but I don't think there's enough. I think a lot more work has to be done on quantum computing, especially in sort of the algorithm area, before it will be that relevant to AI. But it's possible that it might revolutionize AI.
Yeah, I keep kind of trying to visualize the Schrodinger's aspect of the multiple parallel, like multiple instances of the answer to a problem being held at once, and how that would allow a speedier intelligence more than anything.
Yeah, I mean, there are some problems in which quantum approaches are much faster than classical approaches, but they require that you set up the problem very carefully, and that it has some kind of clear objective, like factor this number. And the problem with that in AI is that a lot of problems in AI don't have a clear objective, it's hard to state a clear objective, right? To structure the problems exactly so that quantum approach would work well. So I think that there might be some less rigid quantum algorithms that would really help AI, but we'll have to wait and see.
What are you most excited about? Like in the book, you talked about AlphaGo, and you talk about some of the big projects that are ongoing in artificial intelligence research currently. But what do you think is the most exciting and maybe the most promising?
There's a lot of things. There's a lot of work on what's called unsupervised learning. That's where you have systems that don't require a human to label all the examples, and it learns a little bit more like the way humans learn. There's approaches like active learning, where the system itself decides what it wants to learn, and it uses something akin to curiosity. I think a lot of these approaches are really interesting and could go somewhere. Another thing that I'm excited about is trying to introduce this notion of causality. So this is something that just seems so obvious to us. Like, one event causes another. If I drop something, it will fall, and that's caused by gravity. Or, if I go over and throw a tomato at you, the tomato will splat on your face because that's the way the world works. and there's sort of a cause and effect. But that's not built into computers. Machines don't always, they don't necessarily have any models that take into account causality. So that's something that people are working on that I think is really important. And there's some really promising approaches to that.
What do you think the biggest limitations are? I've heard a lot of people talk about the brittleness of artificial intelligence. But can you talk about what you think are the biggest limitations?
Yeah. So brittleness, meaning that the system, if it's trained on one set of data, sometimes these systems have a lot of trouble generalizing what they've learned to data that's not exactly similar to what they've been trained on. So here's one really striking example of that I talk about in the book. Some of the audience may know about the DeepMind work on Atari video games. So in this work, machines were learned using something called reinforcement learning to play old Atari video games. Things like Breakout, where you have you're using a joystick to move a paddle that has a ball that's bouncing off of bricks and so on. And it learned to play this game at a superhuman level, did much better than the human game player they compared it with. Okay, so, and this is all like it's a video game, it's on a screen. So another group showed that if you move the paddle up by a couple of pixels, something that wouldn't affect a human player at all, the machine could no longer play the game because it hadn't learned the concept of a paddle, sort of it couldn't transfer what it had learned to this very similar version of the game because it hadn't really learned the important concepts. So
it just knew that one very specific instance.
Yeah.
Wow.
So it looked at it and went, I've never seen this before.
Yeah. Said, I don't know what this is. This is something completely new. And so there's this area called transfer learning, which means trying to get AI systems to transfer what they learn to some new situation. And, to humans, that sounds ridiculous because like learning is transfer learning. That's what we mean by learning. So what machine learning means isn't really the same as what we usually think of the term learning to mean, or at least it doesn't yet. So that's one of the big open problems in AI is this kind of transfer learning, generalization, abstraction, has many different names.
Yeah. How do you go from that very specific instance to a general intelligence, right? How do you
Right.
Yeah, I got into a conversation based on a story that we covered recently to do with artificial intelligence. And I made the comment that, well, artificial intelligence is only as smart as its programming allows it to be to a certain extent. And so there's the environment in which it exists, the constraints on that environment, and then the initial programming that goes into it. And someone made the comment to me, well, you have programs now that have emergent behavior that comes out of it. And so isn't that like a generalized intelligence? Isn't that a development of the intelligence?
Well, it depends what you mean by emergent behavior. Emergent behavior can be very non-intelligent.
Mm-hmm.
Of course, intelligence, in us and in living systems, it is an emergent property of our brains, right? Our individual neurons aren't individually intelligent, but collectively they produce this thing we call intelligence. So there is, emergence is an important concept, but it doesn't it's not sort of sufficient for intelligence. And I think, what you said, intelligence depends on the environment. It depends on the initial programming. It also depends on, the sort of experience of the system, the data it's given, or
right.
Yeah. And one of the things that we haven't quite figured out how to do is to figure out what should that initial programming be. And that's something that people are now looking at to developmental psychology to get some insight. So sort of what is innate in babies? They have, or they learn very early on sort of what we might call intuitive physics, sort of how objects in the world interact with each other. And they learn sort of an intuitive psychology. They know about human faces. They know about emotions, about facial expressions. And they have this sort of basic knowledge that they build on. How do we give that to computers?
Yeah. How do you give them something that's not really a blank slate?
Yeah.
It can't be a completely blank slate.
Well, there's been a debate for probably millennia, but in the AI community, at least for 40 or 50 years, about to what extent should we be looking at blank slates versus programming in innate knowledge, and it's an unending debate.
I imagine there are so many, coming from the complexity side of your work, I'm sure there are so many possibilities, that at any one starting point, you have a certain number of possibilities, but you can create a variety of different starting points. You can have blank slates that are allowed to evolve and learn however they may. You can have the partially programmed slates where they have not so many instructions.
Yeah.
And all of them will end up coming to different solutions in the end for different functions and different purposes.
Mm-hmm.
Yeah. Do you think that from, I guess, a theoretical standpoint of artificial intelligence, are there lots of opinions about where AI should end up eventually, whether it should be just something that works for us, something that works alongside us, something that's more than us?
Sure, there's all kinds of opinions, as you can imagine, and there's opinions about what AI could do in practice or in theory. Could we have machines that are actually intelligent, that actually understand things? That's a debate. Or there's a debate about should we develop such machines? Is that ethical? How do we give these machines some sense of morality? Gosh, there's endless opinions in the field. So conferences can get kind of fun with these, debates. People can get pretty, to use a metaphor, hot under the collar.
Yeah. So it occurs to me that, there is a difference whether you're defining this as an artificial intelligence as a form of very powerful calculation system versus if you're looking at it from an almost artificial life sort of setup. Because then, you would want to pre-program, because the pre-programming for responses is very much what instinct is. And it's very much in something that all sort of animal life does in order to survive in this world. Versus something that you want to calculate for a set purpose that might not need any of that stuff. But, and I guess when we're talking about the artificial intelligence in machine form, we're talking about still living on a hard drive somewhere or in a server. Right? We're not talking about implementing this necessarily to physical machines in the world.
No, think about self-driving cars. Mm-hmm. Those are physical machines in the world, and we want them to assist us. We probably don't want them to have their own consciousness. Mm-hmm. But then,
screw you, we're going to the mall.
Yeah, right, exactly. But then there's a question, sort of how far can they get? It's hard to program in rules for driving, for all possible driving situations. So you want these systems to kind of learn on their own how to drive and figure it out in different situations. But one problem is that there's so many possible driving situations that can come up that people are now saying, well, these machines have to have a kind of common sense, like we have, to deal with situations they haven't encountered. But then if you're going to give them common sense, what does that entail? It's all a big open question.
Yeah, what is common sense for an artificial intelligence? Over the years, the history of artificial intelligence, there have been what are called the AI winters, or kind of these periods of stagnation where there's no funding and people are not as excited about artificial intelligence as they seem to be right now. Right now, it appears as though artificial intelligence is experiencing something of a renaissance, a boom, with all the advancement of technology is allowing advancement of the software, the hardware, all aspects. Do you see any indicators anywhere that this is good? This is like the new pace, and this is where it's going to stay, or do you see indicators that there might be another winter on the way?
I definitely see indicators of a little bit of both. So I do think that AI has made more progress in the last 10 years, maybe, than it's made all of its existence. We have all these products now that work quite well in certain circumstances. We have as you mentioned, we have our virtual assistants like Alexa and Siri. We have Google Translate. We have speech recognition that transcribes our speech. We have GPS navigation, facial recognition, et cetera, et cetera. And these things work quite well in most or many circumstances. They're not perfect. They make errors. If they're being used for sort of critical life or death situations, they probably aren't as trustworthy as we would want them to be. So I think those things, if we use them all the time, they're good. But for things like self-driving cars, we definitely have seen sort of the limitations. We've seen expectations been raised to a huge high level. We're going to have we're going to have millions of self-driving cars on the road next year. People have been saying that for several years. We still don't have them.
Yeah.
It's a lot harder than people envisioned. It may be that we don't have what we've been promised, that is true self-driving cars for many decades. I think that's very likely. I think that we're going to adjust what we mean by self-driving, and that we're going to we're going to change the infrastructure of our roads and our cities to assist these vehicles because they can't deal with the way things are now. We'll have something, but we won't have what is promised, and that may have some economic impact. That might be like an AI winter.
It's an interesting one too, because you think of human intelligence as being the thing we're shooting for, and then of course, so what a difficult thing it would be to make an artificial intelligence that can operate a vehicle better, or at least as good as the human, when we haven't done so in any other category. But then you look at when driving goes wrong with humans, it's usually because we're being too human. With our driving. And that's actually this other whole aspect of, we're not necessarily the best model in every scenario to be replicating. So I actually believe the self-driving car has a better shot at succeeding than some, because most of the problems with human driving are very human problems, where we've gone outside of the strict law of the road or programming that we're supposed to stay awake the entire drive, eyes open the whole time, daydreaming while driving, looking in the wrong direction.
Yeah, texting.
Yes, texting. It's something that even if the AI is texting while driving, they're probably okay with it. It's probably a subroutine that doesn't take away from the vision of the road.
Yeah, but I mean, I think our humanness, as you say, we can be very bad at driving sometimes. Mm-hmm. We're very bad at paying attention. And that makes that's also a problem for self-driving, because if we don't, what we have now, or what we're going to have soon, is what they call, level 3 autonomy, which means that the system can drive pretty well most of the time, but in some circumstances, the human has to take over. Mm-hmm. So it's like, the human is supposed to be paying attention while the car's driving itself, because just in case something happens that the car can't deal with. Humans cannot do that, right? They just can't. They're not set up for that. So level 3 autonomy is just not going to work. Level 4.
There's some aspects where they try this already, where the car is going to drive and stay within the lanes. Mm-hmm. And it'll slow down with radar, speed up to keep pace with traffic. Yeah. But you have to keep your hands on the wheel, and it can. There's sensors that will vibrate the wheel if you've let go. But yeah, you're asking a human then to pay attention without that thing you're paying attention being necessarily relevant to them for long stretches. That's even harder to do.
No one can do that. No one can do that. Even like the people that the self-driving companies hire to do that can't do it, and that's been the cause of several accidents. Right? So it's a problem, and I think that the solution is that there's going to be parts of cities that are set aside to have the right kind of infrastructure and mapping and all that kind of stuff that will make self-driving safe, where humans don't have to pay attention, and those cars are not going to be able to drive in all parts of the city or in all weather, and there's just going to be a lot of limitations.
Yeah, a lot of limitations. But I like your implication that the cities themselves maybe, I mean, it feels as though cities are on their way to changing anyway. We have a lot of considerations around transit, and there are a lot of these human policy considerations that are underway. And so this seems as though it might fit right in there. And if people are talking about it all together, how can the artificial intelligence, these self-driving cars be implemented safely within these new plans? Can it work? People, politics, computers, it's going to be a wonderful mix.
Yeah. Yeah, and it's a complex problem too. And then you have to worry about if there's an accident, who's responsible, and all the legal stuff and the insurance. Yeah, it's there's a lot of things to work out.
So there's all this conversation about, from the environmental side of things, that scientists need to stop, staying out of politics and actually get involved because there's so much going on there. But this is the perfect example for this other side of it as well, that when governments are starting to look at infrastructure, and science and technology now need to be part of the conversation. They probably should have always been, but now especially they're really going to need to be part of the conversation. This is another good kind of call to action to have scientists and engineers trying to move into that space a little bit, I think.
Yeah, I think that they are, and computer scientists are kind of waking up to their social responsibility, not just in AI, but in like cybersecurity and privacy and all that stuff, and getting more involved in advising about policy and so forth. But probably not enough.
No. Probably not enough. Like, there's still probably not
enough.
Scientists in charge of certain committees in government related directly to science. But oh well. Baby steps, I suppose.
Baby steps. So tell us a bit more before we finish the interview. Your book, we've talked about a lot of the subjects that you cover in the book, but the idea that it's a guide for thinking humans. What is the intent there behind that title?
Yeah, it was kind of a humorous title because, we talk about thinking machines, and my book is a guide for thinking humans. It's a guide about thinking machines for thinking humans. And I make kind of a joke in the book about when thinking machines might be allowed to join our discussion. But I do, it's also the idea that the book it's meant to be accessible to a broad audience, but it's not like a pop science book that is superficial and doesn't really explain what's going on. I try and explain how a lot of these systems actually work. So it does take a little bit of thinking to read the book and understand what's going on. But I think that's really important if you're going to be evaluating the state of AI and thinking about where machines are, to actually understand what are these algorithms that they're using. So that's something I try and get across.
Which is really important now, especially there are so many. There's the letter that was signed by 150 scientists or people about warning about the future of AI, and there are a lot of public proclamations by technologists and others saying that we need to be afraid of artificial intelligence, and it's the hype machine is pushing to the negative side, the negative perceptions for the general public. And really, the general public needs to be more educated on what's actually happening in the research areas. What is the state of the research right now? Like, what do you really have to be worried about?
Right. So that's exactly why I wrote the book. I myself was a little confused about what the state of the research was. And there's a lot of disagreement about how to interpret the state of the research. So I spent 3 years kind of researching myself what's going on in all these different areas and trying to explain it. And I hope that people get a kind of a good picture of what the current state of AI is. It's constantly changing, but I think it's, certain things change quickly and certain things change slowly. So I tried to capture both of those.
Yeah, I think it's a wonderful book, and you captured my attention right off the bat with the very personal introduction of kind of how you started coming into these questions with a meeting at Google with some of these big minds, and then also talking about. I think it's very fascinating. You bring up your graduate advisor Hofstadter's his fear of his feelings on it, and how fascinating that your advisor, was so concerned.
Yeah, and it's kind of surprised me how concerned he was. and how he was concerned, not for the reason that he was worried that, robots are going to take over the world, but more that intelligence was going to be achieved in computers by what he called cheap tricks. Kind of like the big data statistical approaches that we use now that would sort of capture all the things that he felt were the most human things about us. And he didn't want them to be captured by cheap tricks. So that was kind of his worry.
Yeah, I mean, there are those artificial intelligence programs for music, for art, for writing science articles, writing sports articles. There are all sorts of programs out there now that are doing amazing things, but yeah, to date they are cheap tricks and they are identifiable for the most part. I think there are those few that kind of stand out, but that there is the heart of human creativity has yet to really be touched by artificial intelligence.
Some people would disagree with you.
Yeah.
I mean, they wrote that really weird, uncanny movie script, right?
Yeah, and it's created like visual images that people have called very creative and
creepy.
Sometimes very creepy, yeah. So I think that's another thing people disagree with is sort of what is creativity? That's another one of those suitcase words.
Mm-hmm.
Right. Yeah. Okay.
What is
holding
art?
It all?
Yeah. Yeah.
Well, I don't want to keep you too much later, but I did want to know for the last sentence in your book. Your book has just been released and is out now, but I would love to know if any AI have responded to the question that you ask in the last sentence of your book yet.
Not yet. I'm still waiting.
Okay.
Now we have to read it.
Now you have to read it. Yes. Yeah. The tease. And I hope, I mean, there's a part of it where it would be a fantastic piece of news to hear that you had heard from an AI that had answered
I'm just waiting for an AI to review the book and tell me how it liked it.
There we go. And where can people find you and follow you online? Is there a place where they can find out more?
Yeah, so my website, which is melaniemitchell.me, and my Twitter, which is Mel Mitchell 1.
Mel Mitchell 1. All right, so we can follow you on Twitter and find out all sorts of fun computer science and artificial intelligence news and follow the field. And we can, if you want, you can find information about her book, about all sorts of wonderful things at the website. Dr. Mitchell, thank you so much for joining us on the show tonight.
Oh, it's been great. Thanks a lot for having me.
It's been absolutely wonderful. Really appreciate your time. And thank you once again for writing this book. I hope people do take a look at it. I'm enjoying it a lot. Artificial Intelligence, a Guide for Thinking Humans.
Great. Thank you.
Thank you so much. Have a wonderful night.
Bye-bye.
All right, everybody. It is time for us to take a break. Us thinking humans, we need to take a rest for a moment. But we will be back with lots of science. We'll be back in just a few more moments with more This Week in Science. Stay tuned. Thank you for watching, listening to This Week in Science, being a part of the fun that is This Week in Science. I hope you enjoyed the interview that we just had with Melanie Mitchell. While we are here for a moment, I would love to ask for a little bit of your support. This Week in Science is listener supported at this point in time. And to maintain that listener support, we do need to get your help to make sure we can keep doing that, doing the show week in, week out, the way that we do. And one thing you can do to support us is go to TWIS.org and click on the calendar link. Pre-order a calendar. Blair has finished the art for the TWIS 2020 Blair's Animal Corner calendar, and it will be available very soon. It's open for pre-order right now. You go to twis.org, click on it's a frog, Blair? It's a frog, not a toad.
That's a horned frog.
It's a horned frog. Once again, it's a horned frog. And click on the frog image for the calendar, and you can pre-order your calendar. And pre-ordering the calendar, we will send you one when we have them in. Get your calendar now for 2020. It will be great for you to have a calendar to enjoy throughout the year that has amazing art by Blair. Look at all this wonderful stained glass theme art. And it has dates of important and interesting scientific celebrations throughout the year. So you can always stay on top of really cool celebrations. Like today, it's Mole Day. Happy Mole Day.
I hope everyone had some guacamole.
Guacamole.
Mole Day is full of avogadros.
No, I just went and dug holes in my backyard. But,
mole holes?
Mole holes. Looking for moles. Twis.org, pre-order your calendar now so that we can send you one before the holidays. Get yours before the holidays, before the end of the year. Make your plans for next year on a 2020 Blair's Animal Corner calendar. Also over at twis.org, remember, you can click the subscribe button that will easily allow you to subscribe to iTunes, Google, or our YouTube channel. And you can check out our Zazzle store or click on the Patreon link to support TWIS in an ongoing recurring payment each month at a level of your choosing. $10 or more a month, we thank you by name on the show. Thank you so much for your support. We cannot do this show without you.
And we're back with more This Week in Science.
We are back, and now it's that time in the show for This Week in What Has Science Done for Me
Lately?
And you know what? It's empty.
Huh?
I have no more. I have no more from anyone. I have no more. I have none. If I missed yours, let me know. But otherwise, I have none. Wait, somebody is raising their hand here next to me. Hold on. Hold on. I think we have a recruit. You have something that science has done for you lately? Okay, come here. What's your name?
Kai.
Okay, Kai. What has science done for you lately?
Well, this was a while ago.
Doesn't matter.
But we haven't shared it before.
Share it.
Remember when we got the flowers, but then we figured out that cats can die from lilies, I think?
Right. Lilies are toxic to cats.
Oh.
Yeah, and
I would not have guessed
we
this.
bought lilies for cats and like this thing for my mom one day. And the cats, like, we just found Stella with all this like orange powder on her face, and then we figured out it was actually toxic.
Oh no.
And then we actually had to send her to the vet so then they could actually wash out the stuff. So if we didn't learn that, then Stella and Cappy would be dead.
So I learned something very similar about dogs
and also,
last
I'm pretty
night.
sure other stuff was also poisonous, so we had as well.
Okay, what did you learn, Justin?
I learned science has done for me lately. I went to a conference on animal intelligence that was presented by Franz de Waal, who's a researcher.
Oh, awesome.
Yeah, and I found out that it was a fun story. Dogs, who we think are not disgusted by anything, because they will they sniff other dogs' rear quarters. They will even sometimes eat.
Poop. Yeah, lots of animals eat poop. Yeah.
Yeah. Okay. But dogs are disgusted by citrus because it turns out it's toxic for them. And they had a video demonstration of a dog that licked the citrus. And don't do this at home. There was a disclaimer because it is actually toxic to them. But it had a huge disgust reaction from licking a lime, I think it was, or something like this. And so yeah, there are things that are toxic to animals. Also, what is it? Dogs can't eat chocolate. There are things that will surprise us in the world in terms of what is a toxic thing and what is something that is not toxic to other life forms.
Yeah. And these are things that science can teach us that it figures out. Yes. Thank you very much for that, Kai. I appreciate that. Thank you for joining the show. And if anyone out there has a "What has science done for me lately" to send in, please do send me an email at kirsten@thisweekinscience.com or leave a message on our Facebook page. That's This Week in Science on Facebook. Now go to bed. Okay. Now it's on to some more science news. What do we have to talk about next? Prime editing. You want to talk about some prime editing?
Is that like editing that's just at its prime? It's just so crisp and it's perfect.
Well, it is better, supposedly, than other genetic editing. This is prime editing. It's a new tool similar to CRISPR, a new gene editing system that has been developed by the Broad Institute, David Liu's lab, who was also involved in a lot of the CRISPR-Cas9 system development over the years. They've been attempting to develop a more accurate system because there's a problem with CRISPR-Cas9 is that it's not always accurate. When it chops up the DNA, there are errors, and sometimes there's what are called off-target effects, which is that the gene that you want to put into DNA maybe gets put in the wrong places. And so depending on where it's put, it can have some negative, deleterious effects.
Although I will interject really quickly. There was a big report that was issued recently that I should go find and bring to the show. Gosh, I don't know why I didn't bring it. Where they did illustrate that the viability of those off targets wasn't as big a deal as had been previously reported. Like the deleterious effects aren't actually going to be that bad or noticeable. If you're doing CRISPR in a life form, like it's not really going to be that bad. There's enough random mutation that takes place within the larger genome that having some off-target effects aren't really going to be as negative as we had once feared.
Not as negative, but there's still some negative. And so the accuracy is, if you want to be specific about where you put an edit in our genome, you want a system that's accurate. And CRISPR-Cas9 is just not quite accurate enough for a lot of people's tastes. There have been other developments based on different Cas systems. So there's a Cas12, a CRISPR-Cas12 system that's involved, and a couple of other permutations that have been developed over the years. And there are other gene editing tools like zinc-fingered nucleases. These are also used to chop into DNA and make edits to the genome. But again, it's how well does it work? How accurate is it? And each of these tools is potentially useful in some uses, some situations, but not necessarily all of them. Now, this new precise editing tool, prime editing, as it is being called, they published in Nature this week about the tool, and it uses the Cas system. It doesn't use CRISPR, so it's not the the palindromic repeats of the CRISPR, but it does use the Cas molecule and some other variants to snip one strand. And it follows, the reason it's called prime editing is that it follows from the 3' to 5'. So if you're looking at the chromosomes, they are labeled based on the ends of the chromosomes, as the 3 and the 5, they're opposites from each other. So they're kind of flip-flopped to each other. And the way that it runs is from 3 to 5, and it's called the prime strand. And it goes, the DNA editing stuff goes along that prime strand of DNA. And so the editing tool edits the prime strand. And so it nicks it and just instead of like the CRISPR-Cas9, which cuts both strands of DNA, this new system makes a little nick in one of the strands. And that allows it to put in the edit that it wants to put in. And then the DNA that was there before gets taken away and cut off. And so now you just have a new sequence that's inserted into the genome on that chromosome. And then the prime editor nicks the other non-edited side, just one little nick, and it allows the cellular repair machinery to come along and fix it. And when it comes along to fix that little nick in the second strand, it sees the new sequence of DNA, and so it gets rid of all the unmatching amino acids, all the base pairs that aren't supposed to be there anymore. And so it ends up with the cellular machinery putting in the complementary strand of genetic material. So you're really only inserting half of it. And then the cell itself makes the complementary strand. But anyway, it's supposed to be very accurate, and it's supposed to, they are promising, or they're estimating that it will be able to be used on some 90% of disease-associated DNA variants in our database, which is somewhere around 75,000 variants at this point in time. And so they're estimating that it could have a real huge impact into gene editing therapies down the road for taking these diseases that are genetically based and editing stuff in very accurately. Now, that said, there was a thread on Twitter from a researcher named Jonathan Wild who goes into it a little bit. And he says, okay, this is really cool, but it's also being really hyped up. And the reality of putting stuff into humans and making it work in not even just humans, but living animals is a far cry from having something work in a dish. And their systems and what they tested it on, the cells they looked at in a dish that they worked on it, it didn't work really well in neurons. It didn't work really well in cardiac cells, which are cells that might be really important to do editing in. And so another issue is potentially the size of this system is fairly large. And if you're trying to get it past the blood-brain barrier, how do they do that? They haven't even talked about that yet at this point. They're just at the very, very early stages of saying, look, we have a new tool. We have to figure out how to actually make it work in stuff.
So if it's using, I don't know the mechanism behind this, but if it's using the genetic code or the body's machinery to enact these changes, it makes sense. There might not be the mechanism available to allow a change in a neuron. These are this is a very conserved, very important system. So perhaps it's the underlying machinery that's just not there, which would also be the machinery that would allow mutation to take place, I would assume.
Yeah. So yeah, the machine, and is the machinery going to be there in all the cells? That's exactly it. Are all the cell types going to be able to do what you want it to do? And they don't know that yet. They haven't tested it in all the cell types. So it's making some assumptions. The claims that they're making are based on assumptions that are as of yet unproven. Yeah. So anyway, it's pretty interesting. It's a new gene editing system. I think it just goes to show kind of just how fast moving the field of genome editing is these days. Things are new discoveries, new tools, new molecules. Things are being constantly updated and implemented, and it's really exciting. And also, if people have not seen the Netflix documentary Unnatural Selection yet, I highly recommend it. I watched it this weekend. Very good series on gene editing from the perspective of health from the perspective of environment and also from the perspective of personal, like biohacking. So people doing stuff for themselves. So it takes a lot of different perspectives, and it's a very broad documentary that is created over 4 parts. There are 4-hour-long parts to it. It's really good. Highly recommend it. Gene editing, it's big right now. It's hot.
So hot right now.
So hot. Just like quantum computing.
Mm-hmm.
Oh, yeah, we were just talking about that.
Yeah, we were talking about it. And this week, Google announced that it has quantum supremacy. What does that mean exactly?
It's the quantumist.
It's the quantumist. Yes, exactly. So the definition of quantum supremacy, in essence, is it was originally the concept was originally described by a theoretical physicist named John Preskill, and the idea is that it's a situation in which quantum computers outpace conventional computers by achieving some calculation, doing something that that conventional computers are completely at a loss for, are unable to do. Where it's like, oh, we can't use a regular computer to do this. Guess we have to use our quantum computers. You know, that's the point of quantum supremacy. And so their demonstration that they say is that they had their 53 qubit quantum computer do a simulation that took something like 200 milliseconds for it to run. And their computer's named Sycamore, by the way. Sycamore took 200 seconds to repeat a certain sampling process to do a calculation. And they didn't actually run it because I guess they would have thought it would take too long to run, but they calculated that a state-of-the-art supercomputer would have taken 10,000 years to do the same task. And so because their calculation, they're like, yeah, we win quantum supremacy. Who's going to use a supercomputer when we can do it with a quantum computer in 200 seconds? So, caveat, IBM came out with an article on the archive, and they also came out with a letter, an open blog post to the public about this discovery. And they say, nay, Google is not the most quantum supreme. No, nay.
Quantum drama.
It's quantum drama. Yes. And they say, based on their calculations, which look at other aspects of conventional computing, including data storage, as opposed to just processing power, but also other aspects, they calculate that it would not take 10,000 years, and that a regular computer could have done this same calculation maybe in like 2.5 days, which the quantum computer would still be faster at 200 seconds, but it's not quantum supremacy in this situation because you could still use a conventional computer to solve the problem. And they actually simulate it, and they show in their paper in the archive that, hey, a conventional computer can do this in 2.5 days. So no quantum supremacy, Google. No. And so it is
Google, you need some ice for that burn.
Woo, yeah. But it's really an interesting it's what it is a debate on metrics, and it is a debate on how it is measured, and then also errors. And one of the big things, similar to the gene editing that we were talking about, quantum computing is known to be fairly inaccurate, and it has to repeat things a lot because there's a lot of error inherent in the system. Qubits flip the wrong way all the time, and so the sampling has to be done over and over to get to overcome that bias, that error that's within the system. And apparently Google's system might not be all that accurate and might have a lot of errors in it. And IBM is saying ours is more accurate. It's better. And so it's a fight between the accuracy of the system, how well it can do all those processes, those computations. And then also, what do we define as, okay, what is something that a conventional computer can't do? Because at this point, all of the problems that they are putting to quantum computers are still things that conventional computers are totally capable of. Anyway, it's an interesting debate. It's an interesting point in time where we are. And who knows? I mean, it just means that this race toward quantum supremacy is well underway. And these big corporate behemoths and other technology researchers developing these quantum computers, they're going to continue working on this for quite some time. Quantum computers, they are on their way. And then the AI and all the gene editing, and then it'll be the future.
The future was yesterday.
It was. All right, this is This Week in Science. Justin, what do you have?
I have a cosmological crisis.
Oh no! Do you need a therapist?
Yeah. Huh?
Do you need a therapist?
No, I need an astronomer. Cosmologist at the very least. Astronomers led by the University of California, Davis, has data that suggests the universe is expanding more rapidly than predicted by the standard model. The team made measurements of the Hubble constant, expansion rate of the universe, and came out with sort of different than expected results. They used NASA's Hubble telescope, space telescope, in combination with the Keck Observatory's adaptive optics system to observe 3 different gravitationally lensed systems. And they did something kind of fun, which you would hope that is the way that the science should be done, to rule out any bias of their own, so that they weren't looking at the results and going, if it was only different by this or that, or if we factored this some other unknown factor in, we could come up with the result that we might expect. Instead, they did a completely blind analysis. So during the process, they kept the final answer hidden from themselves until they were convinced that they had addressed as many of the possible parameters and potential errors that they could think of. So they made all of their fixes without seeing what the result of the data was. So then this is the quote from Jeff Chen, who's a graduate student at UC Davis Physics Department. "When we thought that we had taken care of all possible problems with the analysis, we unblind the answer with the rule that we have to publish whatever value we find, even if it's crazy. It's always a tense and exciting moment to get this data." So they did publish, and the monthly notices of the Royal Astronomical Society. The unblinding revealed a value that is consistent with the Hubble constant measurements taken from observations of local objects close to Earth. Which is like the closest supernova that they can make these analysis of. So you say, okay, it's consistent. That's great, except that they were looking at gravitationally lensed systems from really far away. So there is a problem, because according to the standard model of cosmology, the universe was expanding very fast in its early history. So when we talk about this constant, we are talking about somewhat localized events. The further back you go, or the further away a thing is, you should see actually a little bit different shifting than you see close up, because there was a fast expansion and it has been slowing down because of dark matter interactions. What they found actually was consistent. It seems like it's not slowing down at all, that the acceleration of the universe is at least the same, if not going a little quicker than we had expected. So because they're using a sort of new technique and they did all of these blindings, they're going to, of course, do some more looking. But the idea that the value from the local and the distant can be the same in theirs, whereas other observations have also found values from local and distant that disagreed. So there is either problems in the way that we're measuring the expansion, or there is a problem with the idea of the constant to begin with. But it's a pretty interesting find.
I think we've been talking about this for a while, and it's just fascinating that this continues, that every time people look at it a different way, it's not making it fit together any better. At first it was, hey, we measured the cosmic microwave background radiation, and oh, hey, we looked at these supernova things. They're not the same. And then somebody else came in a while later and they're like, yeah, our measurement's not the same either, and it's not close to either one of those. And so we're actually just a weird middle player. And now there's this new measurement that's like, yeah, it's not, they don't match.
Yeah, and it would be just a happenstance if they did, in this case, match, because it looks like they got the same result from the very distant and the close up, that they were, the expansion looks the same, which means not that we're accelerating faster in the expansion, but that it's the same, that it hasn't slowed down, which is, but there's also been this idea that there was initial expansion, everything was moving very fast, and then dark matter slowed everything down, but then dark energy is speeding things up again. So then are we just happen to be at the same point between these 2 points where the slowing down and the speeding up has gotten it to the same point? Anyway, it's fun to know that in a cosmological scale constant, there's still a lot of inconsistencies.
We know nothing.
We know nothing. Our materials are flawed. Our methods are flawed. No constant is constant. We know nothing.
Well, that's the thing, is we actually know quite a bit. And we have quite a bit of data. And the fact that we are finding the inconsistencies in quite a bit of data is really fascinating.
I think it is fascinating. And does it mean that we're going to, if we continue to compile evidence in this direction, will the, dominant ideas about the formation of the universe have to be changed? How much of of our conceptualization of our universe is going to have to switch? Or, we just have to get more data. It's seriously, we are in flatland. We're like, or it's either flatland or it's that the analogy of the blind scientists describing an elephant where
in the dark.
Or describing an elephant in the dark, exactly, where one person says, oh, well, it's this long and this aspect and this, well, it's round and somebody's describing a tree trunk. Someone's describing the
broad.
trunk.
It's like a big wall of a thing.
Yeah.
And then somebody else has got the tail, and it's like, really? Because I've got like a small little snaky thing. And then the guy at the other end's like feeling the trunk. That's a small snake. This is like a boa constrictor. It's huge.
Yep, you've got it. Exactly. So I think we have a lot of, we're describing different parts of things and we need to put them together. But then there's also, the not being able to see the whole picture from where we are yet. And who knows if we ever will, but how amazing that we have the ability to try. We ask questions and we want to know more, and let's learn more. It's awesome. You know what's also awesome?
What?
Blair's Animal Corner.
With Blair.
Oh, thanks.
She loves our creatures, great and small. Biped, millipede, no pet at all. If you want to hear about animals, she's your girl. Except for giant pandas and squirrels. There's Animal Corner.
What you got, Blair?
I have some very smart animals, and these animals in particular are crabs. Swansea University in the UK took common shore crabs. They're also called green crabs, and they saw if these crabs could solve a maze. So they put them in a specially designed maze in order to see how spatial learning in crustaceans work. So that's an important ability in animals that they've studied a lot. A lot of scientists have studied spatial learning in terrestrial animals, but in marine creatures and specifically marine invertebrates, it is pretty difficult to follow those animals around in the real world. And so spatial learning can be complicated to try to study in those individuals. In this study, however, they took 12 crabs and over 4 weeks, they put them in a maze. There was food at the end of a maze each time, and the route to the maze required 5 changes in direction and had 3 dead ends. Over those 4 weeks, the team saw the crabs show a steady improvement in the time taken to find the food at the end of the maze and the number of wrong turns taken. So they were learning the right way to solve the maze. What really was surprising was that when they waited 2 weeks after having solved the maze and then plopped them back down in the maze again and didn't put any food down at the other end, they reached the end of the maze in under 8 minutes, which to them was a clear sign that they remembered their route. So I think one thing is really important to mention here, and that is that since they didn't put food at the end of the maze, they weren't just following chemical signals. They weren't just sniffing their way to the food. They really did remember the right way to solve the maze. And this is something that we have studied in insects before, so it's actually not that surprising. Crabs and insects are both arthropods. They're actually kind of closely related. So the fact that we know that bees and ants can solve mazes and do things like this, it's not so surprising, but it does show proof in methodology for a maze test for a marine invertebrate like this. And it also opens the door to more experiments looking at ocean conditions on crabs, because if we know that they know this spatial awareness and they can learn, then that means that we can test them with some more complicated stuff as well.
I think this is really interesting. I mean, the big thing here, I mean, coming from the earlier conversation about artificial intelligence, coming from questions of different brains and the intelligence that different brains are capable of, and demonstrations of that, the big question that is fascinating to me is how much brain is required to allow this kind of spatial processing and memory. Obviously, this crustacean invertebrate, basically like a glorified insect, has less brain than bees. It's capable of this is a fairly complicated task. Navigating and the environment, right?
And they learned a lot. Yeah. So these crabs that came back 2 weeks later and were able to solve the maze in under 8 minutes, they also took some crabs that had never seen the maze before and plunked them down in the maze. Some of them took almost a full hour to find the other end, and some of them never found the end of the maze in the hour-long study period. So it really did prove that having to find their way through this maze, that they really did learn something.
And there are individual differences in ability, even in crabs.
Absolutely.
Some crabs are just a bit quicker than others. Yeah, I think it's interesting. I'd love to hear a lot more about how the brains of crabs allow them to navigate like this. Let's learn more about crabs.
Yeah, and now we can, because we've proved that they can solve a maze and they can remember things. So, and they can learn from their testing experiences, which means they can definitely be trained to do other things, which I cannot wait to find out what researchers have decided they need to train crabs to do in the name of science. I am so excited.
No, now you're just going to start training crabs. I can see you with a top hat and a little training
crab circus.
I already have a top hat.
I know.
How about it?
Welcome to Blair's Crab Circus.
Well, you know what else would be in my crab circus? The world's fastest ant.
Oh, yeah.
Yes.
What's up with that?
Yes. So this is from the University of Ulm, Germany. They wanted to look at Saharan silver ants. That's Cataglyphus bombicina. And they live in the Sahara, which they sometimes venture out of their nest to look for, they're scavengers, so they are often grabbing the deceased remains of other animals that have perished out on the savannah, and they'll do that in the heat of the day, sometimes 60 degrees Celsius, the sand, which is
hot.
It's fair. It's about 140 degrees Fahrenheit. It's hot. That's really, your tootsie's a blister. But so these Saharan silver ants will go out onto the sand at that temperature. And in studying these ants and just kind of their general behavior, researchers noticed that they were really fast. How fast? Well, after watching them, just going, gosh, those ants were really fast, you guys. They returned in 2015 to film them. And then they spent the past, however many years, 4 years, I guess, looking at the film to kind of discern what's going on with them. They can go almost 1 meter a second, which is so fast.
That is very
so
quick.
fast for an ant. It's actually 0.855 meters a second, pretty close to a meter. And that's the equivalent of about 108 body lengths per second, which, if you're doing some really rough math, that's like 2 football fields for us. Can you imagine running across 2 football fields in 1 second?
In a second.
Sign that ant up to my favorite sports ball team immediately.
That is very fast. And how do they do that? Well, their film found that they were swinging their legs at speeds of up to 1,300 millimeters per second. It's pretty fast. Just kind of whipping their legs back and forth. And so they did this out in the wild. When they brought these ants into the lab, however, at only about 10 degrees Celsius, they were traveling way slower, about 0.05 meters per second.
Because it wasn't so hot and they didn't need to run.
They were going,
their feet weren't getting as heated up.
Yeah. And so the fastest ant before this was at 0.62 meters per second, which is still pretty fast. But they're bigger. So that was only about 50 body lengths. So this is, by body lengths, this is almost twice as fast as that. More than twice as fast. So this makes them solidly, as far as we know, the world's fastest ant. Some other record-breaking animals for speed: the Australian tiger beetles go 171 body lengths per second. California coastal mites go 377 body lengths per second. But these guys are definitely the fastest ants found to date. What makes it also very interesting is that they found in these high-speed videos that their limbs are almost 20% shorter than some of their cousins. So they have shorter legs. You would think longer legs would make you faster. That does not appear to be the case. So it all has to do with their gait. They're actually galloping. They have all 6 feet off the ground simultaneously as they run.
What?
Yeah. So it's like a gallop. Yeah. They might
like a
be
whole
so
new level
fast.
of Mulbridge experiment. Yeah.
So they might be so fast because of the sand dune habitat, because it's so hot, or even more likely because if they went slower, they might sink into the soft sand. So the next step here is to see more about how they can actually physically move so fast, because the lead researcher suspects that their muscle contraction speeds might be close to physiological limits due to their size. Pretty fast. But when we find all of that out, that can actually help us too. That can help us with robotics or other things where we're trying to figure out how to move appendages on tech. So this is something that we could kind of extrapolate to other uses, but for the most part, it's just really cool, really phenomenal.
Yeah, I guess this is a thing with being fast with legs at any scale then, because horses will get all of their feet up off of the ground at some point during their gallop. It looks like it works all the way down to ants.
Mm-hmm. Absolutely. Yeah, it's the same principles.
Yeah.
I am skeptical about the sinking into the soft sand, just given the size of the sand and the size of the ants and the surface area and the weight and all. I'm just imagining ants just kind of float along the top of stuff like that. And
yeah, that's fair.
Find
they
that
can
one,
yeah.
I find that one hard to buy, but the
Yeah.
temperature is
That's a
something
fair point.
more. I wonder.
Yeah, you can make a
So many
raft of
questions.
ants. Ants make their own rafts of each other. They're so buoyant they
They
don't
do.
sink. So you're right. If they don't break surface tension on water, are they really going to sink in the sand? I don't know.
think so.
Maybe it's like cartoon quicksand.
It could be. That's right.
Who knows?
Quicksand.
Who's to say?
Quicksand for ants. I need to tell you about elbows. That's what I need to do. Yeah.
I got two of them.
Do you have two elbows? I have two elbows also. So, if you had a skeleton and you needed to figure out what sex that skeleton is, what would you look at first?
Elbows.
The pelvis. I
Just a guess. Just a guess based on the lead into the story.
Right.
But not typically. What is
the pelvis,
pelvic?
right? Yeah, because
pelvic,
especially
and then-
if they had a baby, the pelvis shifts, right? So that would be a dead giveaway for a female skeleton because they'd have the shifted pelvis.
Right. So the pelvis and usually leg bones, the length of leg bones are sexually dimorphic, which means that there are different forms, different sizes for the male and females. And so forensic anthropologists can use very often the pelvis to determine, or sometimes the skull to determine.
Ribs if you got them.
Right. But it's sometimes, if you're looking at anthropological, archaeological sites, you don't always have all the bones.
No.
And so if you have a couple of factors that you can look at to figure things out, it makes it better. But the pelvis, the skull, long bone measurements, these are all things that have been used historically by these anthropologists looking at these things who are typically from Western countries, and all of the measurements that we've ever done have been based on North American bones and skeletons. And researchers just did an analysis, and they determined that these North American bones do not accurately determine sex for Asian populations. And
You're saying North American, but are we talking European or is that?
It's mostly North American. So
Really?
a lot of these parameters that have been determined have come from measurements of North American skeletons. And that's how we've determined, hey, here in North America, there are, differences in pelvis and skull and long bones that allow us to determine the sex. And based on the fact that many individuals came from Asia across the Bering Strait, they just kind of said, hey, we can apply it to everything. No, they can't. They can't. And now researchers looked at 600 skeletons from Thailand and determined that one new measurement they can make a sexual dimorphism is in the elbows. There are aspects of the end of the humerus bone, your funny bone, right? When you hit your funny bone, the end of the humerus where the elbows, where the bones lock together, then that area has aspects to the shape, the size, the orientation of notches in the bones that are sexually dimorphic, and they were able to create accurate biological profiles that can be used moving forward in Asia that are accurate. And it's great in an area of the world where there are tsunamis and earthquakes and all weather conditions that lead to a lot of people potentially being buried or having been lost, or maybe there are anthropological sites that have come to come into our attention that need to be unearthed. I mean, populations that we need to discover more about, and now we can actually tell what those populations were made up of more accurately. Who knew? All the measurements from North American skeletons weren't applicable to the rest of the world. Who knew? Now we know. Elbows. If you have an elbow bone, you can sex a skeleton in Thailand. Who else has another story? Hey, Blair, you want to tell me a story?
Yeah, sharks. They love each other. Not really though. This is a study from Australia looking at white sharks. We call them great white sharks here in California and Oregon and Washington, on the west coast of the United States. But they are assumed to be solitary predators, but they will gather in large groups when there are feeding opportunities, when there is a group of baby seals or something like that will kind of call to the great white sharks and they'll congregate. And we have found in the past that certain great whites will go to a lot of the same places kind of habitually throughout their life. But it was assumed previously that the groupings of these sharks were essentially random. The individuals just turned up in the same area because they were attracted by abundant food. But looking at photo identification and network analysis, they found out that the groups they hang out in will persist for years. They looked at 4.5 years of photographs of almost 300 sharks, and they found that sharks formed 4 distinct communities, which showed that some sharks are more likely to use the site simultaneously than expected by chance. So even amongst the fact that we knew that there were sharks that always went to the Farallones, for example, just because that's my personal example out here, the time that certain individuals were near one another was more than chance. They were like, oh, hey, Dave, how are the seals today? So they have preferences for who they're hanging out with. So they're actually more, I mean, I don't know if gregarious, that's probably going too far. We don't know if they enjoy being near each other, but they definitely have preferences for who they share their space with, which is pretty cool.
It's very cool. You would often think of them, like you said, as just being these solitary individuals who congregate because that's where the food is. It's kind of coming to the watering hole, the feeding hole. But I honestly, as I mentioned at the beginning of the show, I have never thought of great white sharks as having a social structure of any kind. So this is a bit mind blowing to me.
Yeah. So, I mean, sharks were underestimated once again. And so this is just a reminder that shark research is this huge area that needs help. A lot of people don't study sharks because they have this kind of huge PR problem. But there's so much still that we need to know about these animals that actually need our help. Sharks are disappearing mainly because people don't like them because they think they're solitary, scary killing machines. So the more we can know about them, hopefully the less scary they will be and the better they can do. We want to keep our sharks for sure.
For sure. We love sharks. And Justin, what story do you have?
Last thing I got for today is plants. They're for over 1 billion years. They have been just about everywhere on the planet. They come in very amazing shapes and forms and are as an exotic thing on the planet as can be found. And a project known as the 1,000 Plant Transcriptomics Initiative, 1KP, has put the task to 200 plant biologists to sequence genes for more than 1,000 or 1,100 plant species, spanning the entire green tree of life. And they're announcing some results now. They've just published in Nature. So what they've done is, one of those things that you might assume is already being done now that we have this fantastic technology of sequencing genomes. Of course, we've found the genomes for all these different various plants. But however, the majority of the sequencing that's been done on plants has been done on pretty specific crop species, and tends to get better harvest or better better versions of a crop that is resistant to a blight or a pest of some sort. So this is the first time they just have apparently gotten the biggest data set of genomes from plants just to look at plant evolution and fit plants into their family tree to see sort of what shows up where. And they did find some sort of interesting things. One of the things is that one of the strategies they found, plant genomes, is a lot of plants will just duplicate a gene. Where they had one gene that does something, they now have in the future generations 2, and then maybe 4 sets of the same genes, which seems a little uneconomical, except then over time, some of those additional sets can begin to mutate freely and take on new aspects. Other plant lines they found would work on mutations and modifications to a very subset of genes without doing the whole duplication and adding the entire genome to itself over and over again. So they found different strategies throughout different plant families, which also then starts to allow them to group families. One of the surprising findings was that mosses, liverworts, and hornworts form a single related group, which is actually what was a centuries-old hypothesis that had only been reversed in recent decades. So that whole thing that we do where we start labeling things and start putting them into groups so that we can better understand how they're related and how evolution took place is now possible through this project. They now have a fantastic set of data. So if you're a plant biologist, hopefully you'll have an opportunity to tap into this and compare the plants you have of interest to what they have laid out for you here.
Yeah, I love it when scientists go from just the morphological description to be able to for categorizing and then take the genetic information into account, and it shifts our understanding. So like in the bird world, we've seen all sorts of categorizations shift where species have gone from one family to another, or become their own genus and species, and there's all sorts of interesting aspects. So it's neat, the diversity of life, and it's neat that there's this project is just going and going and going. I was clicking through links on this story, and they're going for 10,000 genomes next, and that's all part of the massive attempt to sequence all life on the planet. And so eventually,
fine-tuning our understanding of plant relationships.
Yes. Fine-tuning all the things. We love fine-tuning. That's what science is about. Big questions, going down to fine-tunings, and all about who we are, where we are in this world. Have we done it?
We did it.
Did we make it to the end? We made it to the end of another show. Thank you for being with us the whole time. Big thanks to Melanie Mitchell for joining us for the interview tonight. Thank you to Gord McLeod for helping in the chat room. Thank you to Fada for helping out with social media and our show notes. Identity4, thank you for recording the show. And I would love to say thank you to our Patreon sponsors. Thank you to Paul Disney, Ed Dyer, Andrew Swanson, Craig Landon, Andy Groh, Ed Stu Pollock, Philip Shane, Ken Hayes, Harrison Prather, Charlene Henry, Joshua Fury, Steve DeBell, Alex Wilson, Tony Steele, Richard Porter, Mark Nazaros, Jack, Matthew Litwin, Jason Roberts, Bill K., Bob Calder, Eric Knapp, Richard, Brian Condren, Dave Neighbor, Howard Tan, Goma K., Donald Mundus, Sarah Forfar, Dan K., Matt Bass, Darwin Hannon, Patrick Pecoraro, Ben Bignell, Jean Tellier, John Gridley, Corinne Benton, Adam LaJoy, Sarah Chavis, Rodney Lewis, Tiffany Boyd, John Bertram, Mountain Sloth, Sotho Gradney, Stephen Albaran, John Ratnaswamy, Dave Friedel, Daryl Myshak, Paul Ronovich, Sue Doster, Dave Wilkinson, Noodles, Kevin Reardon, Christoph Zugnurek, Ashish Panch, Ulysses Adkins, Artyom, Rick Ramus, Paul, John McKee, Jason Olds, Brian Carrington, Christopher Dreyer, Lisa Suzuki, Trim Pro, Greg Riley, Sean Lamb, Steve Leisman, Kurt Larson, Rudy Garcia, Marjorie, Gary S., Robert, Greg Briggs, Brendan Minish, Christopher Rappin, Flying Out, Aaron Luthen, Matt Sutter, Mark Hessenflow, Kevin Parachan, Byron Lee, and EO. Thank you for all of your support on Patreon. If you are interested in supporting us, you can find information at patreon.com/thisweekinscience or click the Patreon link at TWIS.org. On next week's show, we are going to be discussing microbiomes or the lack thereof with Tobin Hammer. And once again, I love this guy's name, Tobin Hammer. It's a fantastic name. Once again, we will be broadcasting live online at 8 p.m. Pacific time. TWIS.org/live. You can watch and join the chat room, join the conversation. But if you can't make it, don't worry because everything's archived. You can find past episodes at our YouTube channel or TWIS.org.
Thank you for enjoying the show. TWIS is also available as a podcast. Just search for This Week in Science wherever podcasts are found. And remember, tell your friends about TWIS.
For more information on anything you've heard here today, show notes will be available on our website. Again, that's www.twis.org. While you're there, you can also make comments and start conversations with the hosts and other listeners. Oh, and also while you're there, you better pre-order that 2020 TWIS Blair's Animal Corner calendar.
While supplies last. Yes,
Or
or you can contact...
5x7.
You can contact us directly. Email Kirsten at thisweekinscience.com, Justin at twistminion@gmail.com, or Blair at blairbaz@twis.org. Just be sure to put TWIS, TWIS, somewhere in the subject line. Otherwise, what will happen to your email?
Spam filtered into oblivion.
Spam filtered into oblivion if you don't put that in the subject line. You can also hit us up on the Twitter where we are at TWIS Science, at Dr. Kiki, at Jacksonfly, and at Blair's Menagerie. We love your feedback. If there's a topic you would like us to cover or address, a suggestion for an interview, a haiku that comes to you in the night, please let us know.
I thought you were starting a rap there. We'll be back here next week, and we hope you'll join us again for more great science news.
And if you've learned anything from the show, remember,
it's all in your head.
This Week in Science. This Week in Science. This Week in Science. This Week in Science, it's the end of the world. So I'm setting up shop, got my banner unfurled. It says the scientist is in, I'm gonna sell my advice. Show them how to stop the robots with a simple device. I'll reverse global warming with a wave of my hand. And all it'll cost you is a couple of grand. 'Cause this week's science is coming your way. So everybody listen to what I say. I use the scientific method for all that it's worth. And I'll broadcast my opinion all over the earth. 'Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. This Week in Science. 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 I've got one disclaimer and it shouldn't be news. That what I say may not represent your views. But I've done the calculations and I've got a plan. If you listen to the science, you may just yet understand that we're not trying to threaten your philosophy. We're just trying to save the world from jeopardy. 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 And This Week in Science is coming your way. So everybody listen to everything we say. And if you use our method instead of rolling a die, we may rid the world of toxoplasma gondii. 'Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. This Week in Science. 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 Got a laundry list of items I want to address. From stopping global hunger to dredging Loch Ness. I'm trying to promote more rational thought. And I'll try to answer any question you've got. But how can I ever see the changes I seek when I can only set up shop 1 hour a week? This Week in Science is coming your way. You better just listen to what we say. And if you've learned anything from the words that we've said, then please just remember it's all in your head. 'Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. This Week in Science. 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 This Week in 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 Science.